In this session, number 12, we'll show you what the spectral lines pop-up is good for, where it comes from, how to use it. On the screen right now, in this box, the highlighted box, we have one of the default lookup tables. It's called XPS Aluminum Schofield. This is the most popular set of sensitivity factors and energies used for XPS around the world. Okay. These numbers were theoretically calculated by a Dr. Schofield. It is possible that your sensitivity factors can be different. Sensitivity factors are shown here. If you follow my mouse cursor, these are the sensitivity factors. Over here are the peaks. Here is silver XPS 3D. And there are also some Auger peaks available throughout the table. Go on down. Let's go down here. Gold peaks. Here are all the gold. Here are the spin orbit couples. These are the sensitivity factors, and this is the atomic number. Right? If you want to modify this table, go ahead, but make sure you modify the number of lines listed here, because the software is expecting a correspondence between the number of readable lines and the number listed here. You can make a brand new table based upon another technique, FTIR, UV-Vis, XRD. It's my intention to make those tables, but I haven't made those yet. So this is one of the lookup tables that you could use for processing your data. If you have a Kratos machine, instead of a VG machine or instead of a JUL machine, you'll want to go in and modify these numbers to match your instrument. Here is a set of the different lookup tables that are available. We have Auger, JUL 7830, a VG 10 kV system. On down here, we've got multiple XPS listings. These are the lookup tables that are available. So these are where all of your other files should be for SDP. All right, let's close that. Move over here. We'll make this bigger. And now we'll open the lookup table. Oh, first, before we can use the lookup table, we have to find and integrate all the peaks. We do that by using this shortcut icon. Okay, the red dots are an intermediate point in the process. If you press the left mouse button, you'll see all the red dots disappear, and you'll see the final integration peaks turn or show up with black lines. Okay, expand this. As we expand it, we're looking for weak signals that did not get integrated. Here's one right here. It was too close to the noise limit, so we draw a little box around it. We hit it with a linear baseline, press anywhere in the background. Now it's integrated. Now we can make a peak assignment for that particular peak. Hit the right mouse button, and it resets it back to normal size. Now let's open up spectral lines. This is what we're trying to talk about. You can scroll along in this fashion, the different elements. You can scroll along by atomic number. And if you're looking for a particular number, you can scroll through the entire table, about more than 1,000 peaks. Okay? We know that this is a native oxide. Our sample description says that. So we've got silicon, we got oxygen, and we always have carbon. So let's pick an element first. Let's pick carbon. The peak position is off a little bit. Maybe there's some charge up, so let's adjust for that. I'm changing the energy offset here, about 4 volts. Now I can say add, so it adds those. Now I want to identify the oxygen. I remember oxygen has an atomic number of 8, so I select 8. And then we add those peaks. And we have silicon. We know we have silicon. Silicon is 14. You can see it selected here. These are the different silicon peaks that are available. Anything highlighted in blue, you hit add those peaks. And we have a peak here about 400. We don't know what that is. I know what it is, but let's pretend like we don't know what it is. So something about 400. So let's go down here to 400 in our lookup list and see what it could be. You think 400 plus or minus 5 volts, so it could be Yttrium, terbium, scandium, nitrogen. That's the answer. But we should also consider some of the other species. Okay, nitrogen is a fairly common material. So we'll select that and it labels it. Now we've got this right here. Again, let's do the same thing. The number here is, all right, I can see it's about 480 or so. Let's go down to 480. 480, what's a likely assignment? Strong signal. Gallium, no. Holmium, no. Tungsten, no. Oh, 10, we got 10. Oh, 10's a good match. Got both peaks there. So let's add those labels. And down here, I know that fluorine appears often on silicon wafers, so that guy right there, that peak right there is fluorine. Add it. And we have almost everything labeled. Okay. Now the next thing to do is go in and turn on the peaks to generate atom percents. Okay. So let's open up the atom percent table. We want to quantify the fluorine 1s, so we put a check mark here. We want to quantify the tin 3D5, put a check mark here. We want to do oxygen, we want nitrogen, we want carbon, and this has no label. Maybe we'll add a label later. And we need silicon. We know silicon is part of this. Anything else? No, that's pretty much it. All right, we can add this to a summary table. If you want to see the summary table, I got to bring it over. We're going to show you more about this later. It lets you take a series of survey spectra and build a table, and you can move things around. It's very convenient and kind. Okay, so but not right now. Let's close that, and we'll close that. Turn on atom percent display, so it displays all the atom percents, and we're done. This is a longer movie. Sorry about that, but now it's finished.